But these are the things I think you should get to ASAP. Don't spend like 10 years learning what a vector is. So they are we have change of basis, we have coordinates, we have RREF, we have matrix invertibility, determinants. For those, there's diagonalization, plus eigen values plus eigen spaces plus multiplicities. And these are all computational in terms of proofs that are pretty standard, because I can't list every single proof. There's like subspace test, linear mapping test, linear combination, like independence test. Yeah, so I think those are leaning towards the second half of the course, but these will like make sure you're prepared for the final, and since the whole thing's cumulative, then if you learn these and speed ahead to these, then you should be prepared for the midterm too. Okay. So I think I would rearrange this. So we'll start with RREF, and I'll skip straight to this. Change of basis. Then I'll talk about matrix invertibility, then determinants and diagonalization. So we have a matrix in RREF. Let's say 4, 1, 0, 9, 3, 2, 1, 0. So, idea of RREF is reduced row echelon form, and there's 3 rules. So, essentially the idea is that you want to get to this. you see each sorry. So you have something like this, and what you want to look at is we have pivots which have only zeros above and below, and each of these rows only have a 1 in front, like the 1 is the first item. And each pivot in each row is to the right of all previous pivots. So in this case, this is pivot, this is pivot, this is pivot. This one is a free variable. So this is a totally different matrix, but with RREF, the way that you get there is you start with like a matrix. This one's a 3x3 matrix. You can do it by 4x3, 2x2, whatever. But the general idea is that you want to use 3 operations. You swap, you like add one row to another, subtract another row, which is adding, or multiply by this constant. So the best way to approach that is look at whichever row you can make it become this. We just care about one being at the left. We want to create that one that we can swap. We can start with any of the rows we want. So in this case, I just want to say this one. We should make that our first one. So it's like, at the start they'll make you annotate your steps. So R3 becomes swap R1, 2, 1, 0, 2, 0. That's kind of messy. And then, or actually, it would have been better to do R2 swap with R1. We put 9 here, 9, 3, 2, 4, 1, 0, 2, 0, 1. And the idea is we want to get this one to be 1. So we do R1 minus 4, R3. So that means minus 8. So we get 1, 3 minus 4 times 0 is 0. 2 minus 4 times 1 is -2. And now we have, we can do more steps in the same one. So let's say we want to swap these 2 rows. Let's do R2 minus 2R3. That means 0, 1, minus 2. And we have 2, 0, 1. And then R3 minus 2r1 becomes 0 minus, oh, zero. One minus 2. Minus 2 to the 9 to 1 plus 4, 5. And we have 0, 1, next 2. And we do R3, 1 over 5, R3. 1, 0, negative 2, 0, 1, negative 2, 0, 0, 1. And what confused me before is that I wasn't sure if I was supposed to remove these or not, because sometimes there were numbers in the top, but that was because they're free variables, and there's not a pivot column. In this case, we want to do R3 and R2 plus R3 times 2. 3 plus R. Yeah, oops. 2R3, 2R3, R1, R2, my bad. And then that means we have 0, 1, 0, 0, 0, 1, 0, 0, 0, 1. So I guess I just got to the identity matrix basically. But yeah, that's the process. And only then can you check rank, which is like in our REF, it's the number of pivots. So 1, 2, 3. So that's row rank, and column rank is, it's the number of leading ones for row rank, and column rank is the number of pivots, and they're equal. That's for system rank theorem. But yeah, this is very important. Grind these problems out because they're used in determinants, they're used in solving matrices. They asked you to explicitly do RREF on the final and midterm, and like rank problems. There's a whole bunch of stuff. So make sure you do these. They're gonna have high ROI. So we covered that one. Change of basis and coordinates. So change of basis is basically when you change your basis vectors, which you should learn in chapter 1. The idea is that you just say we make this one red, this one blue, this one green. The idea is that your basis vectors make up all other vectors in the space. So blue, red, green. Like imagine these are vectors. That's what your basis is. And you can have a matrix in a certain basis. You can have vectors in the basis, just like PB, or you can have an entire matrix. And sorry, let me collect my thoughts. Yeah, you can have a vector in B. You have PB, which is the instructions to turn a standard basis, which is just the identity matrix, into your basis. You have PB minus 1, which is how you turn your basis vectors into your standard basis. You have PBC, which is how you turn like items in basis B to basis C, which is basically undoing basis B and doing basis C. You have CPB, you get the idea. So for these questions, they ask you a few different things. Let's say you want to convert standard basis to non-standard, or non-standard to standard. This is the abbreviation. In that case, you're given either I think you're given PB, or you're given a vector in B, and the formula is V standard equals PB minus 1 VB, or VB equals PBV standard. And what this is basically saying is, if you want to get to a standard base, get this vector into a standard basis, just multiply by the undoing function, undoing matrix, which is the inverse of the doing matrix. Now, the more complicated versions of these are, if you want to get from these ones. So now in those cases, like P, B, C, or B, P, C, C, P, B, you're going to be given a vector and a vector in B, vector, C, vector, and B, P, C, vector, C, P, B. So this one would be, assume we want C, correct? So in each of these cases, it's like, if you're given a vector and BPC, you just like take the vector, we want the vector in C. Well, that's just BPC times the vector in B. And I believe the other way around would be VC equals CPP. And then I think you invert that one. I think. Yeah, that makes sense. If you're given two vectors, so these are BC, B, you're solving, in these cases, solving for P. So in those cases, I forget how to do that. Low key, I don't want to mislead you. Change the basis, coordinates. Oh yeah, and I think that's all I wanted to say. Yep. Matrix invertibility. So, assuming we have a matrix M, this is how we get to something from standard. And so, the opposite of that is the inverse of the matrix. Like, this notation might not be right, but like they do write M and M minus 1. And I'm just like drawing the brackets for my own thing. And the idea is, this is instructions. Oops. Did it die? This is like instruction to standard. And this is like, oops, from standard, instructions to standard. And so a matrix is not always invertible. There's a theorem called matrix invertibility theorem. My pen died. Thanks. And there's like 11 different things you need to memorize. I didn't, but like it's good for proofs. But I think the main ones to remember are that your determinant is not 0. Because your determinant represents the amount of change. And if it didn't change, then I guess you can't undo it. But if it did change, you can undo it. Also, you want to remember that it's full rank, because you can only do this like with independent vectors in the basis or something like that. Full rank. That means column and row. And what else? There's a few other ones. I remembered them a few days ago. I don't remember them anymore. But yeah, this is good for proofs. But how do you do it is the question. How do you invert a matrix? There's two methods. One of them more for teaching. This is the one that they'll teach first. This one is to do 1 over determinant times adjugate So like a minus 1 equals this. The other method is Jordan elimination. It's where you take a and in the identity matrix, you perform RREF and make sure to update this one too. And at the end, you'll have 1, 1, 1, 0, 0, 0 on the left side, and you'll have the inverse of A on the other side. Because every step you do to turn this one into identity matrix is the reverse step to get it to... Basically, you're showing all the reverse steps you're doing in order to get from A to the identity matrix. It's pretty cool. And this one, I keep forgetting what adjugate means, but adjugate is the cofactors I believe transposed. Can you check what the adjugate of the matrix is? J U G A T E of the matrix. The transpose of the cofactors, I got it right. So in the cofactors, which I should have mentioned earlier, are they're basically numbers. They're its own matrix that I'm not really sure what it means, honestly. But the way that you get it is you take A 1 4 9 3 2 1 1 0. You hide this one, take determinant of this, and place it here. So that means of our cofactor matrix, it is 2 minus 0, so that 2 goes there. And repeat that for all 9. I thought that was very useless, but you have to tell you your adjugate. You should learn more about cofactors. I will later. And this one is the faster and standard method of doing inverses. Sometimes this one's faster for small 3 times 3 and below, but Jordan elimination is by far the better version. Oh yeah, I just did the determinant, but I didn't show you what that means. So the determinant, where you take matrix A, and denote it as determinant A, or if you have your full matrix written out, you put like, instead of those 2 brackets, you put just these lines. For 2 by 2, 3 by 3, those are the main versions. You have like 2, 1, 0, 4. What you do is you multiply these minus these. For 3 by 3, 1, 4, 3, 2, 1, 2, 0, 1, 9, 0, 1, 8. They'll teach it to you like, oh, you take this one, ignore these, find determinant of this. And then, that would be first value. Then you subtract This one, the ones it basically like in chess, with like a rook, whatever ones it hides. Minus that determinant plus, oops, delete this, delete this, plus you want to add this one, and whatever this one crosses out, take this one, put it here. And the reason why we do that pattern is because it looks like this, which is from cofactor stuff for some reason. I also forgot to mention inverse of a 2x2. Is you swap take these, swap A and D, and you invert and you subtract B and C. But yeah, this is determinant, and it helps a lot with different stuff, especially diagonalization. Like a lot of proofs rely on determinants. It basically shows how much change has been made in a vector space with a transformation or something. So there's different types of matrices that have different determinant strategies, and I'll make another video on that. Diagonalization, eigenvalues, eigenspaces, multiplicities. These are try and mark questions. Like on my final exam is worth like 8 marks out of 50. That's a pretty big chunk. So let me make a new page. Can you search up diagonalization problem? Not all matrices are diagonalizable, so I want to make sure I have one that is. So there's actually a few steps to diagonalization. There's finding eigenvalues. And then find eigenspace for each. And then check multiplicities and fill in D, P, and P -1. So let's say we have a matrix -1, -2, 2, 4, 3, -4, 0, -2, 1. What we want to do is, when we see this and we're asked to find these things, start off by writing P or C, whichever one you want. Whichever one you want. This is the characteristic polynomial. Equals, oops, what happened here? pressed user guide by accident. Determinant of A equals, determinant of A minus lambda I, where lambda is an eigenvalue, with eigenvalues being the amount that an eigenvector is scaled by, and an eigenvector being the vectors that in the matrix, when you transform them, they maintain the same span. So we take minus 1 minus lambda, 3 minus lambda, 1 minus lambda, minus 2, 2 minus 4, 4, 0 minus 2. This is our determinant that we're looking for. And see, look, there's a trick here. We could do it from this default method here, but that means we need to compute all three of those. Or we can do it from the side, which I didn't know that until this year. So that's plus minus plus. That's let me move over. Minus 1 minus lambda times determinant of 3 minus lambda minus 4 minus 2, 1 minus lambda minus 4 minus 2, 2 minus 2, 1 minus lambda equals and this is 2 by 2 determinant, and this is 8 minus 8 minus 4 minus 2, 1 minus lambda minus 4 plus 4. And you compute all this like as you know, now we're trying to find the solution to this using typical algebra. So it's like 3 minus 3 lambda minus 1 lambda is minus 4 lambda plus lambda squared minus 8 minus 4 times minus 2 plus 2 lambda plus 4 can I move it off page? I guess I can't move it off the page, but minus 3 plus 4 lambda minus lambda squared plus 8 minus 3 lambda plus 4 lambda squared minus lambda cubed plus 8 lambda plus 8 minus 8 lambda minus 16, and then take all this and then take all these. Yeah, that's annoying. plus 8 minus 3 plus 4 plus 5, which gets us 1 lambda cubed plus 3 lambda squared plus 5 lambda. Oh wait, actually it's plus 9 lambda plus 5. And then we factor that with like 1, I don't know, like maybe 1 is it? 1, so minus 1, 1, minus 1, 2, minus 1, 7, minus 1, no, so maybe negative 1, negative 1, 1, 4, minus 4, so that's 5, yeah, negative 1, 4, minus 4, 5, minus 5, 0, so we get lambda minus 1, and maybe I just did unnecessary steps. You can like optimize it, but then we have negative 5, 1, how do we get this? What? Anyway, the idea is that we find the factors. Am I doing something wrong here? Oh. I didn't eliminate these ones, did I? They were off the page. Oops. So we'd actually have this gone. And this would be negative 3. So negative 16 plus 8, so minus 8. Minus 8. So this would be minus 3. Which would become 3 minus 3 plus 4 is minus 1. Minus 3. Which screws with all this. Hopefully I can find it fast. 1, minus 1, 3, minus 1, negative 3. Minus 1, minus 1, minus 1, 1, minus 1, 2. Okay. So let's say 1. Minus 1, 2, 2, 1. Oh, so it must be minus 1. 1, 4, minus 4, minus 5. 2. Minus 2. 2, 5. I swear. Negative 1, 1, so minus 1, 2, 1. Oh, that would only work. Minus 1, minus 1, 1. I'm tripping balls. Yeah, this is not cool. I should not be fucking this up. That's how you find eigenvalues, eigenspaces. I'll show that, even though this kind of broke. For each eigenspace, for each eigenvalue, we do a minus times I. So we sub this in. So then what we do is we get the matrix that looks like that. And then what we do here is we solve for RF. If there's free variables, we say like y equals t, and then get the other ones in terms of x, y, z, in terms of each other until we solve the equation. And then we write vector v equals t 1, 0, 1 plus, if there's another one, u 1, 1, 0, etc. And then these become this, whatever this is, equals basis of these two. This is not the index, this is the actual number, the actual eigenvalue. And then we check, we do that for all, we check multiplicity. we have AM, GM. So algebraic multiplicity is the number of power in the original factor. So like, let's say we actually found factors here. This one's squared, this one's not. This one would be 2, this one would be 1. For geometric multiplicity, it's how many are in here. So we should always have geometric multiplicity is greater than or equal to algebraic multiplicity. If it's not, then the matrix is not diagonalizable. There's a word for it. I forget what the word is. If it's valid, if all of them pass the check, then we do is we find P D P minus 1. I think this is like I'm not sure if it's A on the left side or whatever, but this is the formula. And so P is all of our what is it? All of our eigenvectors, where D is the values, zeros, and P inverse is just the inverse of P, I believe. We'll have to verify that, but it should get you pretty close. And last but not least, subspace tests and stuff. These are standard proofs. There's obviously non-standard proofs that you can't expect, but you can expect to have these ones. So how do I paste? Okay. I'll just undo all that. Subspace test, linear mapping test, and independent test. Linear independence, usually for basis, spans full space. None are combinations of each other. Oh wait, that's for checking if it's a valid basis, but that's not what we're talking about. Linear independence, though, for a basis, by definition, it's just like it spans the space, and it's stuff about linear combination and stuff. So you just need to know how to do those. Subspace, check existence of zero vector, multiply, like it's vector addition or scalar multiplication all persist, and it's a subspace. This one's tricky for me because they change it up sometimes, but like the idea is the same. I just don't know how to apply it always. And linear mapping, you just use the equation to check, like, given linear equation, this is LCX plus LDY equal to CLX. Oh yeah, sorry. cx plus dy equals clx plus dly. That's what we want to check. So this was like kind of a mid brain dump, but it should get me back to where it needs to be for math 235, and I can make it better one if I want.